Hello, this is a new RBMK video. It has been a while without videos, so I will just try to start the simulation at the 100% power and try to run it until I run out of fuel and eventually see what malfunctions appear during this period. So I will not be using the latest version, which is the port full game version. I will be using the previous one to that, which was by Itchy-Avocado. So it has malfunction, it has saving and restoring. Let's open it. So it's a version 2.162. Okay, let's open the absorber, rod control and fuel monitoring. The emergency, no, we won't need the emergency core cooling system. It's already in auto, I will close it. Reactor power regulation. Turbine control. Loop 1, this is the reactor recirculation pumps control, and loop 2. Let's look at the schematics too. So you see basically a functioning RBMK nuclear power plant. You have the two pumps to the condensate cooling system, two hot well pumps on, two feed water pumps on, and two pumps out of three in each loop of the recirculation in the core. So everything looks fine to me. Just to make sure that there are no malfunctions that we are not aware of, I will cycle through.
Tell me something. Have you looked at the reactor fueling schedule?
Yeah. I will cycle through the pumps that are on, meaning that I will turn on the pump which is off and turn off the second one. So to do this, we need to open the inlet valve. Just a reminder, to turn on big pumps, you need the inlet valve open and the outlet one closed. This to avoid cavitation because of inertial effects. So once the inlet valve is at 100%, we turn on the pump. We do it in parallel in both loops, just to save time. And then we can go ahead and open the outlet valve.
Your steam dump control valve to the condenser has failed. Put it in manual, operate it manually till we can get it fixed.
Okay. So steam dump control. I didn't open the pertinent panels yet. This is feed water. And steam dump control. Where is it? I really forgot about the functioning of this simulator. The aerator pressure control. Reactor drain. Condenser. Steam dump control, it's here. Okay, so let's see if there is a problem here. We switch to manual and back to auto. And yes, there is a problem, so we click on repair it. So we save $1,800 by fixing it by ourselves. I will open to the reactor core status, which gives us very important information. We see voiding, we see fuel temperatures, we see xenon concentration, we see flow in both halves of the core. Okay, you see the core reactor level going down. That's not good, and probably it has something to do with the feed water pump. So let's turn on the pump number 3. Same procedure as with the main recirculation loops. We open the inlet valve. You see it opening slowly, 35%, 45%. And once it's at 100%, we will switch on the pump. Hopefully that solves the problem, because you see the reactor is going dangerously low. We risk uncovering fuel assemblies and damaging them. Okay, this does not seem to be the problem, so I will switch the jam level control to manual and back to auto. Low reactor level.
You've got low drum level in the reactor. What?
I will try to find by myself. So what else can cause this problem? You have the reactor drain control. Let's switch to manual and back to auto. Yeah, here was the problem. So repair it now. And we save some more money by fixing things by ourselves. Okay, so things go smoothly. Generated load is a bit low. So that's because the main valve is not at 100% opening. What I will do is to manually decrease pressure set point. So let's go to 1500. This in imperial units. So I will switch to metric to be accurate to the Soviet Union units. Okay, so units to metric. And now this is at 10,000 something kilopascal. So let's go to 10,000. You see valve control opening to match this pressure set point. Everything is smooth enough, so I will make a big jump to 9,000. Voiding is slightly low at 17%. This is because I have 3 pumps in each recirculation loop on. I will switch off the pump number 2 in each loop. So off, and close the outlet valve. Close. This is something that will be handy later, because we'll run out of fuel and we'll have too many rods withdrawn, so we'll lose the controllability of the reactor. So increasing voiding will allow us to be a bit farther into running this reactor without refueling it, because the purpose of this video is just to refresh the functioning of the reactor for myself, because I didn't use it for more than 1 year. So if you are already familiar with this simulator, you can just skip this video and probably wait for new videos. Okay, so things go back to stable. Valve control is at 92. Let's go to 8,500 kilopascal. Meanwhile, I will open some more panels. Feed water system. And condenser system. I will also cycle through the condensate pumps. I will switch on the second one. And switch off the third one. Acknowledge the trip. Valve control is at 95%. And now we will switch to manual. Once we are close to 8,500 kilopascal. Okay, switch to manual. And now we don't have any more a control problem in which we have this target value. Now we fix the opening, and this is what we control. So I will manually continue opening the valve control signal to have the main valve opening to 100%. While you do this, you should check the trends that they don't go out of the chart, like reactor level, etc. But because
Have you used your fuel monitor?
Because they are quite okay, I can just go to 100% and forget about it. We are set to run this reactor at optimal efficiency because we don't have losses because of drag in the main valve of the main steam line. Generator load is at 1060, but we are probably running some potential power from the pressure of the main steam line. So when this goes down, you see this value here going down and it gets to a stable value. is when we will get the real long-term generated load here. That probably will be around 1040 megawatts or so. Okay, everything is running smoothly. We have 3 feed water pumps, which I forgot. We can turn off one of the 3. Let's turn off the number 1. And close the discharge valve. Okay, so now everything is good. 2 out of 3 condensate pumps, 2 out of 3 feed water pumps, and 2 out of 3 in each loop recirculation pumps. You see voiding is at 22%, so slightly above what we had before with 3 pumps on in each recirculation loop. So it went from 17 to 22, 5% more voiding. And this gives us a bit more of reactivity because, as I said, this is a positive void coefficient reactor. It means the more voiding we have, the more reactivity, which is the contrary that we see in pressure water reactors usually. This makes this reactor more economical, meaning that we can run it with less enriched fuel. And we also need less powerful control system because by itself the reactor can reach criticality more easily. But it also means that at any controllability problem, it's more difficult to stop a critical runaway, because when it starts having a critical runaway, the reaction becomes exponential because you have a positive feedback loop. You have more heat that creates more boiling, and the extra voiding creates more reactivity. So you can see this is a positive feedback loop. So that's why the control system, a robust control system is critical in this kind of reactor. Okay, generated load seems stable at around 1035 megawatts. Now I will go back to auto control, but to do this, okay, I will do this. I will go to auto, but you see immediately it's closing the main steam valve control, which I don't want. So I will decrease pressure set point to 7400 kilopascal, and hopefully this will assure 100% opening of the main steam valve. So as far as we have a drum pressure above the pressure set point, we'll have 100% opening, which is what we want. Okay, so everything looks good. Trends are stable. If we wanted a little bit more of power, we could always reduce consumptions, like the steam we're using for the deaerator. If we reduce pressure set point here, a little bit more of steam will be available to spin the turbine. But I will not do this because the aerator is critical to keep the quality of the water in the reactor. Okay, fuel burn up is at 53%. Probably we can run it until around 45%, and then we will have many rods withdrawn and we will progressively lose controllability until you see the neutron flux dropping to 0. When this happens, this will be interesting because it's different of what we see in a Scrum or like a program shutdown, in which you like suddenly go from 100% to 0 power in maybe a few seconds. Here you will see a gradual decrease. It will be fast, but it will also be gradual. Like you won't see any sharp angles here in the charts when this happens. In this scenario, because you don't have a reactor scrum, you don't have a turbine scrum either. So a turbine will keep spinning as far as we provide pressure to the turbine. And because I set the system into auto, this valve control will progressively close as the reactor is providing less and less heat to provide steam to the turbine. So overall, this will be a smooth process in which the fuel burn up will govern this slowing down of the turbine. Actually, this is not quite realistic because the fuel burn up is quite accelerated compared to reality. Probably this is like 100 or 1000 times faster, burning fuel faster than in reality. So this decrease in power will be much faster than in reality, but still we will see that it is progressive and we have still a working turbine during this process, which will last for a few seconds. I think I didn't do this in any of my previous videos, so even if this is a catch-up video or a warm-up video, I think this is new in my playlist. So that will be interesting. Okay, fuel burn up at 50%, we're at half of the life of this fuel, but we didn't start at 100%, so it's not half of the time of the entirety of the video. Okay, so during this time I found a German engineer who has a interesting personal website, and he made a tutorial of this simulator after he found my videos. So I advise you to look for his website. I think it's hartrusion.com. He has interesting posts about restoring motorbikes. He has an old 125cc Aprilia and he restored it. And he has a very good tutorial of how to operate this reactor. I think it's better than my videos because it's more like systematic. Like he doesn't forget any point and it's very precise in the definitions. So if you have some trouble understanding the function of this reactor and my videos are not enough, go to his blog post about RBMK reactors and you will find all the information. In addition, I think he works like I'm not sure if I would say, maybe I will say stupid things, but I think he works in the energy industry, so he must know more about this subject. Okay, so fuel burn up 48%, and very strangely, there are no malfunctions. I think malfunctions are turned on. Like, yes, time step, and metric system.
Have you used your fuel monitor lately to check?
Yeah, I did. The reason why I don't want to use the fuel monitoring now is because it's quite buggy still in this version, so there is a big chance that if I use it, I could cause the simulator to crash, so we will not use it. Let's just cycle through the condensate system control. Let's cycle also through the main recirculation loops.
Are you aware of the fact that loop 2 has low flow?
Okay, because just to be fast, I didn't wait for the pump to turn on to switch off the other one, so that's why we created this dip in reactor level, which create a cascade of perturbations in all the other systems. That's fine. I didn't open the legend of the trends. Where is it? Yeah, here. Yeah, so the red one is the reactor level. The yellow one, drum pressure. Keep an eye on neutron flux because this will be the interesting one. When fuel burn up goes below some 40 something We are already at 45, so we are close to that. We didn't get yet the alarm of too many rods withdrawn. We'll get this first. And there we go. Too many rods removed. You see the rod position is around 13.8%, 13.7%, and the center core is at 0. So we already have the full power, let's say, in the center core. So we totally withdrawn the rods in the center core. And now we're controlling the reactivity by controlling the rods in the peripheral. So now they are at 13.0. Fuel burn up at 43.8. 12.8. Okay,
you just lost reactor recirculation.
Okay. Pump trip. I don't know if I left it like that when I cycle or it was really a trip that happened now. It doesn't matter. Low main steam temperature.
You've got low flow. You just lost a reactor recirculation pump. You're going to start void.
Yeah, it seems I lost a pump here. So, very bad timing. Really bad. Okay. Repair it now. I'm about to run out of fuel, so I don't want to be dealing with recirculation pumps now. Okay, so voiding increased when I had only one pump, so probably this helped a bit with reactivity, but now I turn it on again. Alarm. High voiding in loop 1. Yeah, so this high voiding probably helped. You see the withdrawn went a bit back to 11%, now it's back again to 10%, so it's critical. Now there are really too many rods removed from the core, and don't worry, what's going to happen, it's already expected. Neutron flux will go down fast, but in a controlled manner. And we will still keep controllability of the turbine during this process until we trip everything when things go down to 0. But as I said, because we keep auto control of the main valve steam control, we will keep controllability and we'll keep producing energy during the fuel gets exhausted. So we're at 9%. I think it's at around 8% that we will have the drop in neutron flux. I'm not sure because xenon now it's quite low, but from my experience with the Chernobyl accident simulations, this happens at around 8%. Probably now we'll be able to be a bit lower because of the extra reactivity, because of less poisoning. If you want to know about the accident, look for my video in which I recreate the accident. There is a thumbnail with Diatlov and the AZ5 button in red. It's in my last videos. And now we are at 7.8%. I think it's imminent. The drop in neutron flux is imminent, so keep an eye into the trend chart. It's the cyan line, so it's this one, neutron flux. Valve control, so keep an eye into the charts, keep an eye into the valve control signal, which is at 100%, and keep an eye into the control rod position, which is at 7.1% now in the peripheral, 0.0 in the center core. This is quite critical. We almost have no control rods in the core. So remember, if now we were to press the scram button, this could cause a critical runaway because you remember the positive void coefficient.
The steam jet air ejector is screwed up. You better get down there and do something quick, because if you lose vacuum, you're going to trip this turbine and shut us down.
What's the problem? Steam generator what? I didn't understand him. Oh my god, this is really bad timing. Why things break down when I have no fuel left? I didn't understand. He said fuel generator what? Steam generator? Repair condenser, repair air ejector. Heat exchanger loop 1. Maybe. I don't see any problem. All trends are stable. We're down to 5%, so really the lower xenon really gives some extra controllability, some extra reactivity, because from my experience is at around 7% that you have the loss of controllability. And now look at the neutron flag is going down, but you see it's like a continuous line. It's not like a drop to zero suddenly. It's going down, and look at the valve control. It's decreasing 93%, 91%. The turbine is still spinning. Neutron flags, it's almost at 10%, and generated load is still 700 megawatts. And look at the drum pressure. The valve controllers cannot keep up with the decrease of thermal power. Cannot keep up. It's not closing fast enough. Drum pressure is too low. We have many alarms. Everything is wrong now. And look at the neutron flag is increasing back. That's very dangerous. We can have a surge. Neutron flag is increasing back. And it's back under control. For a moment you see neutron flags went down almost to zero. Here the reactor is almost stalled. And then you have a surge of neutron flags probably because of voiding that went very high because of low reactor levels and low recirculation. And you see the two emergency core cooling pumps turn on. And I will acknowledge all the faults.
You've got low drum level.
Okay, whatever. I will repair it by $2,000 now. And you see
The reactor's going to scram.
It already scrammed, man. You see that very interesting neutron flags line. We had this gradual decrease here,
You got to get the.
in which the turbine tried to keep up
Have you?
by closing the main steam valve control, but it could not, because I was checking the drum pressure and it was decreasing much below 7,000 kilopascal. It was like at 4,000 kilopascal. So we can say,
One of the primary.
oh, it's very annoying now. It will throw 1,000 prompts. Let's pause it a second. Where is the pause button? Ah, here. Okay. I paused it a bit late because now we don't see the start of the neutron flux decrease trend. But you saw it. Neutron flux started decreasing very quickly as fuel get exhausted. Then the valve control tried to close to keep the pressure at a correct point, but it could not keep up with the rate of decrease. This is probably because simulator is not realistic and the decrease is too fast compared to reality. In reality, you should perfectly keep up with the decrease of reactivity because of fuel burn up. And then when the neutron flux was at around 5%, it seems, this value here, it went up again. This was very scary because it looked like a surge because of uncontrolled boiling and a positive feedback loop. But luckily, when it arrived to this level, probably the core cooling system pumps or the recirculation pumps could bring some water into the system, and the reactivity went down again. And probably at some point around this scram happened, because I see the reactor is in trip mode now and the control rods are at 46% insertion. So taking into account that the full insertion of the rods takes 30 seconds, so probably this happened 50 seconds before this moment. So probably happened when the neutron flux was at a alarmingly low level, or probably when the steam pressure went below some critical point around 3,000 or 2,000 kilopascal. And it may be that this surge is caused by the positive void coefficient combined with the graphite tip of the the control rods. I don't know. I didn't have time to look at everything in live. I will check the replay of the video. But eventually the controllability was regained, and you see this decrease of neutron flux, and then the reactor level is recovered, and you see there is no fuel cladding damage. So everything went well. There is no accident, there is no critical runaway, and there is no radioactive contamination. Okay, this was supposed to be a very routinary video, but at the end it was quite interesting. I hope you enjoyed it. See you in the next video. Bye.